Well, that was quite the introduction. Thank you guys very much for coming out. I hope you found this to be very helpful. What I want to sort of accomplish today is give you some sort of sense of where the different jobs are in industry, and then talk about some of the sort of the key skills that I look for when I'm hiring somebody for a data science role. And they're not obvious in a lot of your school training, but a lot of you have these characteristics. And I just want to make you aware that you have them so that you can sell yourself that you have them during an interview, and it's just not all about the textbook knowledge that you have. So I'll skip the slide of who I am, because Harry did a great job of that. So what I'm going to talk about is some different types of data jobs, and the definitions around a lot of these jobs are very murky and muddy, and you talk to somebody else and you'll get a different set of jobs, but I just want to make you aware of the sort of the breadth of jobs that you had. A lot of these jobs don't have underlying degrees that you go and get. Like, if you want to become a mechanical engineer, you study mechanical engineering. If you want to become a data engineer, I don't know of any university program in data engineering, right? So how do you get into that job? What is even that job? So what I want to talk about is different types of job categories, and I'm going to leave out large swaths of job categories, things like biostatisticians, financial modelers, informatics. I haven't worked in that field, so I'm not an expert in it. So just there's this whole thing I'm not talking about that may be your thing. Across different industries, you'll hear different titles, and you look at the job, and they'll look radically different, but they'll have the same title. And my general suggestion to people is don't look at the job title. What we call an analyst on the East Coast, we call a data scientist on the West Coast. Look at what characteristics they're looking for in the job when you're applying, which makes it a little harder to search because you have to search for broader terms and stuff like that. But there's lots of jobs out there. So I'm going to focus on jobs that are largely in the statistics, analytics, computer science, and STEM fields. Let's start with data analyst type jobs. So these are basically jobs who have sort of generally a specialization. So a business analyst does sort of standardized reporting, sort of standardized metrics, and have an expertise in the business operational side of things. They understand the business terms, they understand what the decision makers want to know from a business point of view. Then we also have business intelligence engineers, and the job almost sounds the same. So business intelligence engineers, they are trying to gather intelligence about the business. So did this metric go up? Or maybe we should segment these customers and market to them differently, where an analyst doesn't tend to do that. Business intelligence engineers tend to have more of a CSE background. They tend to work a lot with data pipelines and SQL, where business analysts tend to have tooling around Excel, that type of stuff. It doesn't necessarily mean that that's the exact tooling you need. I'm just talking in sort of broad generalities, what type of jobs and what type of schooling they would have for these things. So there's no schooling for business intelligence engineers. A lot of business intelligence engineers have the same schooling as business analysts. They can have sort of a CS background, they can have a stats background, they may have a business admin degree, that type of stuff. The focus is slightly different on where they operate within the company. Data analysts, business analysts, tend to operate more on the administrative side of the business, where business intelligence engineers tend to work more on the back end side of things, supporting internal business decisions that are happening at a lower level. Again, these aren't any rules, just sort of general rules of thumb. And then we have data engineering type jobs, and these can be like a database administrator. So their job is to run a database and keep it up and running and help you optimize your query and set the security permissions and do auditing. They do things like we have a database, but that database is overloaded. So how are we going to scale that? How are we going to shard it? Are we going to separate it out? Are we going to have read-only shards where you only read from this database, but then how do you replicate the data over? They manage things around failing over of databases. So we may have a database, but if that database goes down, is there another one that will pick it up so the business stays up and alive? They don't tend to be experts in the data that's in the database. They are experts in keeping the system alive, scaling, performant, responsive, and that main thing is called ASA compliance, that you have a replicant database and it has the exact same information. Then you have database engineer, which sounds like a database administrator, but the job is actually very different. Their job is to focus on building products that use the database. So you may have enterprise resource planning software. So that's all stored in a database, and you would have tools around like, we need to order this product at this time because there's a 6-week lag time that from the supplier, and we anticipate that we'll use up our supply in 5 weeks, so we want to order a week ahead. So that's enterprise resource planning. They write the tooling around that, managing all that information, managing all the relationships between the data. And then you have a data engineer. And a data engineer is basically a plumber. They take data from one spot, move it to another spot, which kind of sounds simple, but it's actually a very challenging role. How do you do that when you have a terabyte a second of data coming into your system? Or where you have streaming data. So every time you move your mouse on a web page or click on something, that's generally getting streamed back to a server. How do you capture all that data and you don't lose it? How do you move it into systems that can write it and read it fast enough? How do you run aggregations on it so that it's actually in a useful form? Like, I don't really care that you move your mouse to the right, but there's maybe some analytics that we would want to do on that. So they build out all those pipelines to move the data around. They also tend to be experts in where the data is. So I work for Amazon. We have data, right? We have no shortage of data, but it's actually one of my challenges in my job is, where is the data? Who has the data? How do I go get it? How do I get permission to do it? What does it actually mean? So data engineers tend to have that local expertise for your domain because that's what they do all day long, because they're doing the plumbing and they need to know where the plumbing comes from. So they don't necessarily need to have the detailed understanding of like, this is what this data means, but they need to understand like who has it and what's it rolled up to. Is it rolled up in daily events or weekly events, that type of stuff. So if you have a strong CS background and you want to get into the data side of things, this is a great job. If you love infrastructure and developmental operations and stuff like that, this is a great job that most people don't know about. We're also starting to see an emergence of a new type of job called a machine learning engineer. And you talk to 11 people and you'll get 14 different definitions of what a machine learning engineer is. But the idea is that basically you're a software developer. You don't have, I'm going to put air quotes here, the sciencey background, but you understand machine learning models, how to use them, but not necessarily how to create new models or how to build new algorithms. But your job is you're going to plumb the data, you're going to help stand up the models. So a lot of data scientists aren't software developers. They can write code well enough. How do you take that code and we're going to put it in production and we're going to have to handle 100 transactions per second? Well, I use R and R is going to do that. Right? So they specialize in that type of thing. They also monitor performance. So we may build a model and their job is just to monitor because maybe the system underlying is changing and they want to go back to the scientists and say, hey, this model is not performing like it used to. Maybe we should go back and look at refreshing it or something like that. And they also ensure computational efficiency. It's very expensive to run a lot of these machine learning models. And small changes in the way you build your system will allow you to scale, but also how much you pay. And then in the jobs, in the science sort of job families, I'm going to lump them together into two categories. So there's economists, and I would classify economists as specialized data scientists. They tend to have very strong skills around analyzing messy, dirty data, that type of stuff. They tend to have very strong mathematical skills. But the industry hasn't sort of lumped them into a specialized version of data scientists. They tend to be separate. But I work with a bunch of economists. They have very similar skill sets than I do. They just know the economic side of things much better than I do. But like the overlapping tools is very common. I don't think it's a big transition from an economist to roll over into sort of a generalized data scientist. So then data scientists. So 4 years ago we had a discussion on what data science is. I still don't know. It is whatever you want it to be. I'm going to talk through some different types of data science fields, sort of ways I classify jobs based on what I've seen listed on job postings and stuff like that. But I think one of the key things behind a data scientist is that you have a bit of a hybrid education. You are a statistician, but you also understand some machine learning. You're a communicator. You're also a domain expert in a particular area, but you also have coding skills. You have to get to your data, and the data is changing. Generally, I can't work on data that fits in my laptop. Right? I generally can't work on data that fits in a big, beefy cloud server. So I need to have CS skills to manipulate that data to get it into a form that's usable by me. So I think this is a very cheesy infographic. And if you Google infographic data scientist, you'll find this one. And I think it's actually a very nice summary of the core skills that you should have. You don't have to be an expert in all of them, but you should develop skills in all of them. So math and statistics, that's the bread and butter. What I do notice is a lot of people, and some coming from like a CS background, they have machine learning skills, but they're really weak in the statistics. And I think you need to have machine learning and statistics. If you're going to pick one, pick statistics. The machine learning is kind of fuzzy stats with sort of social theory behind it. But it really, really helps to have that statistical mindset. And I think in this group, that's really sort of our big card that we go when we're looking for a job, is that you're an expert in statistics, and knowing some machine learning is great. You should also have good programming and database skills. I get so much work done in SQL because the compute's there. It's easy for me to pull down a small data set. But good coding skills. You don't have to be writing like optimized code and know all the fancy computer science data structures like linked lists and graphs and stuff like that. But you need to be able to code in a way that's reasonable and efficient, that you can get your work done. Communication and visualization. At the end of the day, we're trusted advisors. We're taking complex statistical ideas, complex analysis around the data where, things are fuzzy and uncertain, and we're used to thinking about confidence intervals and stuff like that, and you have to communicate that to people that are generally not technical. And you have to communicate it in a way that's meaningful for them so that they can act on it. And if you just give them all the technical details and there's nothing actionable there because you didn't communicate the idea, you may as well not come to work that day. Your job is to help them make those decisions. So communication is very important. And then I think what you need to grow into, you don't have to start with this, but you have to pick an area that you're going to become an expert in. So when I switched over my job title to data scientist, I was in San Francisco, and I became an expert in web application security metrics. And that's what I did for 5 years, and there's like 4 of us in the country that do this. Well, 3 now. It's a very, very niche area, but if you want to know about web application security metrics, I'm your guy. That's my domain expertise. If you want to ask me about marketing information, I don't know much. So pick an area that you're interested in and really dive into that, because at the end of the day, you're going to become the expert that they're going to come to for advice, and you need to know that domain really well. So very quickly, I'm going to say that there's sort of 3 categories of data scientist jobs. So there's the generalist. So the generalist is somebody that's highly skilled in math and statistics. They really think with a statistical mindset. They tend to have a background in statistics, like a formal educational background in statistics. They're used to working with complex analysis and helping you to just decide what type of decisions you're going to make from your data and how you're going to interpret those results. They conduct research projects at a generalist level. And what I mean by that is they're not an expert in a very specific field of research, but they are experts in experimental design. So you may have a marketing person come to you. This category of data scientist may not be an expert in marketing, but they understand enough about experimental design that they can work with that expert in that domain to help them come up with an experiment that's actionable. They do a lot of creating of visualizations for communication. They drive data insights. So they're working within the organization to say, like, let's not use your gut. Let's go figure this out using data. So they're the ones that's really advocating for that type of role within the company. They develop scalable algorithms and models. And by here scalable, I'm not talking about like large-scale production systems. I'm talking about I can do this analysis and then I can repeat the analysis. I want reproducibility in what I do, so I don't want to have something that if the data changes because I need to rerun the analysis this month, that I have to go back and start all over again from the very beginning. I want to scale it out so that I just make minor changes or just click go and run the analysis and reinterpret. Basic programming skills is all you need. I highly suggest you get good at SQL because most data in the industry is still sitting in SQL databases, relational databases. But then pick an analytical language like Python or R. I suggest you kind of get good at both, but pick one of them that you get really good at. And you don't have to know all the fancy data structures and stuff like that. You just need to know what you need to know in order to do data manipulation and analysis and visualization and stats and stuff like that. You don't need to be able to build web pages generally. They often use point-and-click tooling, like Tableau and stuff like that. I think that's somewhat all right, but I don't think it's scalable. It's a powerful tool for getting quick insights. The technical abilities required, you can learn Tableau very quickly versus learning R or Python. But I think you should strive to move past that so that your work is reproducible. And learn these other general programming languages as well. But it is useful. I'm not trying to knock it at all. Then a research science type of data scientist. So here they have a deep expertise in a research field. So generally what we're seeing is people that have quantitative backgrounds. So people with backgrounds in physics, engineering, neuroscience versus math, statistics. So they're used to working with really messy data and working with a lot of ambiguity in what they're doing. And they are skilled in statistics and machine learning. They tend to have a little bit more machine learning than the generalist, but a little less statistics. So I would say a physicist is generally good in statistics, as an example, but not as good as a statistician is. They focus on the research aspect of the problem. How do we figure out how to do this? What novel approaches can we use? How do we parse the problem? How do we rephrase the problem? How do we do something that nobody's ever done before? Where the generalist is doing a little bit of that, but it's kind of just the same with a slight variation. The research scientist tends to be working on stuff that's very novel, very new. There's a lot of ambiguity in the problem that they're working on, like what is the problem that we're actually really trying to solve? How do I figure out a path to solve that? It's not just go read the literature and replicate what somebody else did. We're doing new innovative things or trailblazing. Their output is generally proof of concept. They're generally not writing stuff that's going into production. It's like, we can do this is how we would solve it. And others would then go and productionalize that. And they often have a little bit more intermediate coding skills. They tend to be working with larger data sets, messier data, where the generalist tends to be pulling stuff more out of like the SQL databases, where the research scientist tends to be pulling more stuff out of like logs or JSON files or scraping the web or something like that. Because it's new, we haven't built the infrastructure to capture the data. Then there is sort of the machine learning expert. These people typically have very strong educations in computer scientists. They tend to have very strong coding skills. What separates them is that they are an expert in machine learning. Their statistical knowledge, often not that great, but they are able to create new machine learning algorithms. They're able to get into the fine details and really tune a model and get that extra 1% that's going to earn you $1 million. That's really, really hard to get. They understand not just the math, but the computational side of things. So a lot of the models are very expensive to train. So how you set that up, you can drastically improve your training. The quicker you can train, the more you can iterate. The more you can iterate, the better your model will get. So they tend to be experts in that. They tend to work in a fairly well-defined problem space. So they would do things like, we want to do face recognition. We want to track somebody in a building. We want to scan a barcode on a package on a conveyor belt. The problems are fairly well-defined, where the research scientists, the problem's not well-defined. Part of their job is defining the problem. And that's less so the case in the machine learning classes of jobs. They have a basic understanding of stats and experimental design, but they're not experts in it. So who are the clients for these scientists? So I try to push the concept that data scientists are not the decision makers. They're the ones that are trying to help people make decisions. Because if I make a decision, I impose my bias. I'm a scientist. I try to not have biases. I have lots of biases, but I try not to have them. So our clients are the product owners. These are the ones that we're taking direction from. We work with them to figure out what's possible. There's a lot of like, we'll just do data science. We'll just do machine learning. And I call that insert magic here. It's helping them figure out what it is that we can do, what are the decisions we can make. We work a lot with software developers to help them go from a rule-based system, which is the way they tend to think, to a machine learning type system where the machine has learned the rules. Software developers write a bunch of if statements, switch statements, and loops to write the rules. And we're trying to replace that with something a little bit more fuzzy, and that's the machine learning model. So you work with them, you have to learn to communicate with them, you have to learn their lingo, they have to learn your lingo. And I think this is where the machine learning engineering job family is really going to take off, because they sit there nicely. They understand me when I talk to them, and I understand them when they talk. Where it's harder to do that with a regular software developer. Management is also one of your big clients. I think one of the big roles for any of these data jobs is to help the decision makers make the decision. So it's getting in there ahead of time and saying, hey, let's instead of going with that, let's go get some data on that. Or let's try these different tests so that we can figure out what to do. And let's not just do the tests, let's figure out ahead of time what the criteria is going to be for us to release that product or not release that product. We also help them to decide the scope. Something like, oh, let's go do this, this is a great idea. Is that really going to impact the customer? Is that really going to drive revenue? Whatever your objective function is. So going and saying, well, before we decide to spend all this money launching this project, let's do some data science around this and get some ballpark figures around how big of an impact. Because if we're doing this, we're not doing this, and there's this opportunity cost. And maybe this, maybe not as cool or interesting, but maybe that's really where we should be heading, because that's where the impact is going to be. So it's helping them make that decision. I also think that data scientists really need to work in a community. I do a lot of different talks. I run an R meetup. I talk to different universities. Within my job, I do a lot of training. And I think it's very important for us to do that so that we can expand the general knowledge of how this stuff works, how you make decisions with data, how you can improve general processes by analyzing what's going on, as opposed to just like, I think this is a problem, let's go fix it. We also have, in our science training, you tend to be very isolated. I worked in the lab, and I kind of knew what the other people in the lab were doing, and they kind of knew what I was doing, but there wasn't a whole lot of collaboration. But science works best with collaboration. So when I went to Amazon, one of the things I started was a data science excellence program, which is basically just getting scientists together into a room to talk. We do peer reviews. We help out other teams that don't have generally access to scientists to build that community. And it's been a huge benefit, I think, for the organization, because I now know people all over the place within Amazon. And when I have a problem in an area that I'm not an expert, I generally know who to talk to. If they don't know the solution, they know who else to talk to. And I've become much more productive from that. And scientists have this insular mentality around the way they work. And I think we really need to get out, get to know each other, and expand our capabilities by networking, by sharing what we know, teaching other people. I'm sure everyone in this room is an expert in an area that I have no knowledge in. So I want to get to know you so that I don't necessarily have to become an expert in that, but when I have that problem, you can help me. And I can help you, because I know things that you don't know. So let's expand our capabilities as opposed to always being limited to solving problems with what I know and thinking the way I think. So what tools do I use? I try not to focus too much on the tooling for my job, other than I want to use the right tools. So I typically use R for statistical modeling and visualization. I think it's a great tool for data manipulation. It has some problems, but it has some great advantages. I use R Markdown a lot because I very much believe in the reproducibility of my work. If I get a 5 for an answer somewhere, I should be able to backtrack where that 5 came from. If my data changes, I should be able to recompute right away. And now that 5 is a 6, I should be able to go back and diagnose why that 5 is now a 6. I use Python for NLP and neural networks. I used to have just neural networks and NLP there. R now has great packages for neural networks that I haven't used a whole lot, but I'm starting to use it there. I use Perl for text processing. I don't recommend anyone really go learn Perl. It's a very cryptic, weird language that is heavily reliant on regular expressions. But for text mining, if you've gone through the process of learning Perl, it's amazing. So I don't tend to do my text mining in R or Python. I use Perl for that because it's the right tool for the job. I use things like Elastic MapReduce, which is basically Hadoop and Spark, Elasticsearch, which is a big search engine, and I make very, very heavy use of SQL. I strongly recommend people learn to write complex SQL to do analytics. It pushes the load onto the server so it's not running on your machine, and frees up your machine to do other stuff. You can run multiple databases, run multiple queries. And I do a lot of stats in SQL. I've actually, at one company, I put R into the Postgres database so we could actually run R code. There's something called PL, procedural languages, that all databases have that allows you to run other languages in it. So we would, all the data sitting in the database, it would run R code to run a survival model that I had and not have to like call or build infrastructure. So some of the soft tools, communication is very important. The ability to write and share your ideas. At the end of the day, you're going to try to convince people that what you're saying is the way you think we should go based on the data. And if you can't communicate that either verbally or in written form or by doing presentations or teaching them why this is important and why that's not, or why that thinking is not statistically sound and that you should be thinking this way. I notice there's a lot of magic around p-values. People have this, oh, it's 0.05 and the world is wonderful, it's true. That's not really the case. The p-value is like, well, there's probably something here. That doesn't mean that it's true. So just communicating that type of message to people that aren't literate in statistics in a form that they can understand is very powerful. I believe in influence without power. I try not to make decisions. I try to influence your decision. Your being the client, right? They have a different perspective than I do. And I try to help to guide them in the direction that the data is saying we are going. There may be other business concerns that is not related to the data, and I shouldn't be forcing a decision that's not taking that into account. That's their job, is to make the decision. Mine is to influence them and guide them into making the decision that the data is telling them. You should also be very logical and analytical. Parse what people say. Try to understand what they're talking about. Don't take assumptions on face value. Be a little pedantic. Be able to break problems down into simpler things that are actionable. And one of the biggest challenges we have, I think, as scientists, is actually defining the problem. Somebody will give you a problem statement that sounds simple and easy enough, but it's not really like a hypothesis statement, or it's not actionable, or you can't put objective measures on it. Like, we need to increase revenue. That's not a good problem. There's nothing that I can do there. I have to go and redefine that problem for them. And that takes a lot of communication skills and working with people that aren't used to thinking in that way. So I want to talk to you a little bit about some key skills that I think we should be always striving towards developing. So there's this concept called design thinking. It's very popular in the design community. And I'm trying to push that we as data scientists start implementing our own version of it. So I'm going to start with a bit of an example. So I used to work for this company that hacked websites. Big companies paid us to hack them. It wasn't the other way around. And they had a problem that they had customer churn. So people would pay a lot of money for a one-year contract, and at the end of the contract, they wouldn't renew. And it's a very long cycle. It took about a year to get a customer on board, and then we would have them for a year and then they would leave. Right? We're going to make our money by having them long-term, because it's so expensive to bring them in. So in design thinking, I'm going to walk through this problem using sort of a design thinking approach. So we're going to have these different stages, and these are cyclical. Don't look at this as like a linear operation. But we're going to have empathy for our customer. We're going to try to understand their position, what their real problem is. We're going to then define the problem, and then we're going to ideate on possible solutions. We're going to then build out some prototypes, and we're going to test those prototypes. And at each one of these stages, we can go back and reiterate, and loop back to the previous one or two before that, whatever we learned along the process. And I find this to be a fairly systematic approach. A lot of people start with a solution, like, oh, we have this problem, random forest will work. And what I want you to go is like, no, back up. That's in the ideate phase. Let's really clearly work on defining the problem. Let's define and understand what the customer needs are. So the customers are churning, but why? Think of it from the customer point of view. So one of the things we do is we give them a long list of vulnerabilities. I'm going to occasionally use the term vuln, which is the lingo for vulnerability. So a vulnerability is like an insecurity in your website. So we give them a long list of vulnerabilities. I'm talking like 500 vulnerabilities on a website. It's fairly typical. And what they thought they were getting was a security program. They thought, like, hey, we don't know how to do web security. We're going to hire you. You're going to show us how. But we just give them, like, here are your 500 vulnerabilities. Have a nice day. They don't know which websites to target. So large organizations can have hundreds of websites. So what are the ones that I should go after and fix? A lot of times organizations don't even know the full scope of the websites that they have. You have 500 vulnerabilities on your websites. Well, I'm not going to fix 500. Like a really, really good customer would fix 50 in a year. So which ones do I fix? Tell me that. I can't fix them all. We're going to give them new information about new vulnerabilities as they change their website. But how useful is that information? I have 500 I'm not going to fix. Thank you for telling me I have another 20 more. I'm not going to fix them either. So we have this high churn rate. So now I'm trying to understand the problem from the customer's point of view, where the business statement was, we have churn. If you notice what we have here is, why do we have churn? I'm thinking about the customer. What is it that we're not doing? What is it the customer thinks we should have been doing? Now I can start addressing that type of problem. But I still need to define the problem. I don't have a clear definition of like fixed churn. That's not actionable. So in design thinking, there's a concept called wicked problems and tame problems. I much prefer the terms ill-defined and well-defined, just from like a math point of view. So a wicked problem is a problem that's not well posed. Why do we have churn? Not a well-posed question. So in the define stage, what you're going to do is you're going to work with your customers and reframe the question. And the onus is largely on you to work with them to define what that question should be, and your job is to make it an objective question. Something you can go and test. So a wicked question is, how do we reduce churn? That's not actionable. I can't do anything with that. It's poorly posed. A tame question is, what mechanism or features can we add to the customer such that they would renew, given the fact that they have more vulnerabilities that they can fix? So the question has become one of identification. What are the features or mechanisms that I'm going to go after? I've now reduced the whole churn problem to the single observation that they have more vulnerabilities than they can fix. I didn't take on all the problems. Now, I may have multiple tame statements, but I've just turned this one into one problem that I can now actually go and work on. I don't know the solution at this point, but I know what I'm going to limit my scope to in my analysis. More vulnerabilities they can fix so that they don't leave. So ideate. Go talk to the experts. I don't have a monopoly on bad ideas, but I certainly have a lot of them. Go talk to people that have all kinds of good ideas, people that are working in that field, that really understand it. So what I did is I went and I talked to our in-house hackers. I talked to top security experts. I talked to CISOs, which are Chief Information Security Officers. These are the guys that are ultimately responsible for security. I talked to the customers, and the customers meaning the engineers, the engineering management, the people that were responsible for tracking and compliance of the vulnerabilities. And then I went to talk to people in different fields, outside of web application security, because there's overlaps here between what I'm doing and what other people do. So I find ancillary fields that have similar problems, but look at it differently. That's going to give me a new perspective so that I can innovate as opposed to just doing the same old, because the same old largely hasn't worked, which is why we have the problem. Get as broad a possible perspective of what you're going to do. Notice at this point, I haven't said I'm going to try random forest. I don't even know what I'm going to do at this point. I'm trying to figure out these paths forward. Read the literature and read patents. So literature is great. It tends to be very narrow in focus. Patents tend to be a little broader in focus because they want a patent to cover as broad an area as possible. So go into Google Patent, search for patents in that area, and just read them. Like if you want to sleep, it helps. But read them. They often have summaries. Patents often have like the key innovations. You can just skim that, decide if you want to read the whole patent. Steal other people's ideas. I mean, give them credit for it, but like it's easier to take what somebody's already thought and developed and just modify it for your needs than it is for you to invent the wheel. Brainstorm your ideas. Once you have a whole bunch of ideas, go back to the experts and have them tell you what's wrong with it. You might have an idea that you think is perfect, but you just don't know something, and the experts say, well, this is why I don't think it will work. And you're like, oh, okay, I never thought of that. So once you have buy-in from the experts, go back and ideate again. Go back to the experts until you sort of settle on like, okay, this is really making sense. I'm having a large group of people say that this is a great way we should go, and then sleep on it. I rarely had my first idea be my best idea. Give yourself some time to think about the problem. So the idea that I came up with is I'm going to create a security metric, basically a FICO score for your website. And so what problems is it fixing? Well, the engineering teams, they have hundreds of vulnerabilities. They don't know what to fix. So with a security metric, I can tell them which ones to fix first. Whatever ones are going to drive your score to a better score, those are the ones you're going to go fix. Just like when you're fixing your credit score, right? You know, if you have an overdue account and one that you're paying on time, that you're maybe overpaying, go pay the one that's overdue. That's going to fix your score much. You don't want to game the system to give you the best credit score. We want them to game the system to make their website more secure. Engineering managers had a problem with like, how do we evaluate a security program? We're going to put all kinds of resources into it, I don't know if that was worth money. Should I train my employees? How do I evaluate that? Now they have a metric. They can go and say, our score went from this to this, the program was successful. They can put objectives on it that the manager gets held to. Okay, if we're going to give you the resources to train your engineers in security, we want our score to go up by 10%. And that's what we're going to call a success. The CISO, the Chief Information Security Officer, he's wondering about like, what site do I fix? I have hundreds of websites. Well, you go fix the one that has the worst security score. The executives, it's nice and simple. They understand what you're doing because they can relate. You give them a message. It's like a FICO score, your credit score, for your website. That's all they need to know. That's the level that they're operating on. But now I've communicated a very complex idea to them. And they go, oh, okay, that makes sense. I see the value in that. So then I ideate. Well, now I use my data science skills. How do I do this? So I use something called survival analysis. And so survival analysis is you have an observation and then you have an observation that you may or may not have. So like grandma falls down, breaks her hip. 6 months later, is she alive? That's what I want to predict. Well, she may have died, and I observed that, or she may have gone to another doctor, and now she's censored. I don't see that. But I saw her at 3 months, so I knew she was alive at 3 months. So we have the same problem with vulnerabilities. A vulnerability is created, or it's fixed. Or a vulnerability is created, and we lose them, and we don't know what the effect was. So maybe 4 months later, the contract ended, the vulnerability was still there. Did it ever get fixed? I don't know, but I have some information. So I'm going to use survival analysis for this. I also decided that the underlying system of the web security changes a lot, so there's going to be no absolutes. The whole system is going to change. As people get better at security, the metric will get harder to raise because the general standard in the world has gotten better. Everyone has vulns, so I'm not going to penalize you just because you have a vulnerability. What I'm going to do is I'm going to reward your behavior. I'm going to, if you're fixing your vulnerabilities quickly, I'm going to reward that. If you fix your vulnerabilities slowly, I'm going to penalize you for that. I'm going to also base how much I trust you on how much I know about you. So the longer I've been scanning you, the longer I've been assessing your website, the more I know about you, so the more I trust you. So this is getting back to the churning, right? You're starting to see there's reasons why people would want to keep using these metrics. We have games in it so that, well, if you want to up your score, stay with us longer, renew that contract. And then if I don't know something, I just assume the worst. I assume you're a bad actor. So then I build prototypes. And I use abductive reasoning for this, as opposed to deductive reasoning. What I want to do is I want to start really simple, and then move on to the next little incremental thing that's just a little bit better, and there's an uncertainty around it. Deductive reasoning says, I come to the conclusion this is the truth. Abductive reasoning says, well, no, I'm still wrong, but I'm a little bit right. And I'm a little bit more right than the model that I had before. So I'm going to start with a simple model that's just your standard vanilla survival model. And then you start looking at your data. So here I have a graph that says we have a number of vulnerabilities along the x-axis, and along the y-axis is how often you remediate. And I look at the data and go like, okay, if you have under 50 vulnerabilities, you tend to remediate or you tend not to remediate. Like it's sort of all over the board. If you have more than 50 vulnerabilities, you'll see that you have a whole lot of white space in the upper right-hand side, meaning that you don't tend to fix your vulnerabilities. You just go, I have 500, I'm not doing anything. What does it matter? I fixed 50, that's all I can do. I still have 450. But if you have 50, you may do it or you may not. And so then you develop a hypothesis around that. You do some more abductive reasoning where here along the x-axis I have time, and along the y-axis I have basically customer ID. And our customer IDs are incremental, so you can think of it almost as time. And the green dots is that they are credit card compliant. The red dot is that they're not credit card compliant. But then if you notice at the very bottom, you see this like vertical line below 10,000 in 2012. There was a problem with the data. Oh, that changes my model. I was going to look back historically. Now I can't because there's a problem with the data. Then also use abductive reasoning. So one of the things we measured was how dangerous an exploit was and how easy it was to exploit. So that's called the threat and the severity. And I thought, well, this would be really important. Like if it's really easy to exploit and it's really dangerous, then we really should weight that. That should be really important. But when you look at the data, the big red blob in the top right-hand corner says that pretty much everything is easy to exploit and very dangerous. So I can only make differences when there's differences. So, like logically thinking, this should be one of the most important metrics that we have. It turns out because there's no variation, and it's the variation that I need in my models, it's not important. Don't necessarily put it in. Also look at the scaling and dive deep into your data. So the top graph is the amount of CPU time that we utilize for a scan versus the length of time for the scan. It just looks like there's this big black bar. So that we scan fairly quickly and we fully utilize the CPU. So the CPU utilization is, sometimes we can scan, sometimes we can't. So if you have a retail website, we're not going to scan you on the weekend, because that's when your traffic is. We're going to scan you like Tuesday morning, because that's when you don't have much traffic. But if you dive deep into the data and go, like, oh, as opposed to like, just like, oh, okay. The graph below, what we're starting to see is we're seeing these arcs in the data. And what that's showing us is that people were playing games. They weren't letting us scan their websites. So it may take me 100 hours to scan your website in a month, and you're going to give me 5 hours a month to scan, because you don't want me scanning your website, because then you're going to tell me vulnerability and I'm going to have to go fix it. So diving into your data and trying to figure out, like, how am I going to solve that problem? How am I going to move forward? I'm not going to completely solve it, right? I'm not going to get these people to allow us to solve the scanning issue. But how can I make it a little bit better? Other things like the graphs that we're showing here is the different service levels that we have for what we provide, and whether or not authentication is needed, and whether or not we can authenticate. So PE is the professional edition. It's the most expensive. And on the top graph, you'll see that the green is that almost every PE website we have to log into. These people are paying a lot of money. And if you're looking at the bottom graph, you see the PE website. There's a lot of websites that they won't let us log into. They're paying us a lot of money to scan their login page. Dive into your data, understand what's going to happen, and then think of a way. I'm not going to solve that problem. They're not going to give us our credentials. But how can I game it so that I can make a model that's a little better? So I'm going to end up penalizing them for this in their security score. When they come back to us and say, oh, my boss says I need to raise this score, I'm like, give us your login credentials. You've now motivated them. So you build your models. You build prototypes. You understand the empirical relationships. You draw lots and lots of graphs. It's very common for me to draw hundreds of graphs and look at my data. And then you build simple components that you can understand and then expand upon. And then you live with the idea that all models are wrong, but some are useful. So George Box said this from the box plot thing. And I think it's very important. Your model represents reality, but your model is not reality. So I hear people say, it's a good model, it's a bad model. I always kind of recoil with that. Is it a useful model or not a useful model? And you start by building a bunch of models that aren't that useful, and you incrementally repeat over and over again so that they become more and more useful. You get it out of production, you learn from it, and then you go back and you fix it. And you test your model. So on the graph here, what I'm showing is two models. One is where I went and I fixed a data error, but it's very, very expensive to fix that data error. Like we're talking thousands of man-hours to do it, versus not fixing it. And the models, no real difference. So even though it would be better, it's not worth the time and effort, right? All models are wrong, some are useful. The one with the data error is still useful. Let's go with that. And then we test. Simple, small releases frequently. Don't spend 6 months building a model. Spend 2 weeks building a model. Send out your null model, because that's better than what you had before, and then make it a little better. Make it a little better. Rinse and repeat, the whole process over and over again. So I showed you at the beginning the survival model that I started with. This is the final model that I ended with. Not simple, but it was built in an incremental process. Run the model, find where I can improve it, make the model a little better. Don't try to start building this. You'll never get anywhere. So the design thinking, Think about your customers. Define your problem clearly so it's actionable and objectionable. Then identify all kinds of different ways that you can go and solve this problem. Talk to the experts. Build a bunch of prototypes. Build a bunch of bad prototypes. Test them. Refine. Repeat. Over and over and over again. So, what do data scientists typically do? We are trusted leaders that help people make decisions. Influence without authority. Don't confuse the tooling with the job. My job is to help people make decisions. If I use machine learning, I use machine learning. If I use statistics, I use statistics. If I use a scatter plot, I use a scatter plot. Whatever is going to help carry that conversation forward. Advice on how to launch your career in data science. There's no single path. The field is too new. But most importantly, have a scientist mindset. And that design process that we went through is a bit of a scientist mindset. Have a solid foundation in statistics, statistical thinking. Some basic machine learning is great. If you want to go down the path of like the machine learning data scientist, great. And have really good machine learning. Have fundamentals in programming. You need to be able to get to your data. If you can't get to your data, then you have problems. Excel, great. Use Excel a bunch, but Excel nowadays is very limiting in what I can do. Pick a statistical programming language and get really good at it, whether it's R or Python. Be able to communicate complex ideas clearly and concisely. Know your audience. When I talk to an engineer, it's different than when I talk to a product manager, which is different when I talk to a director. They have different concerns, different points of views, different ways I phrase things. It's not for me to tell them, it's for me to communicate to them and for them to understand. I need to communicate in the way they understand. Get experience with real-world data sets. In schooling, it's all curated, the data's all there, it always works. That's rarely the case. So try some Kaggle data sets, but data sets are curated. Go to UCI has a machine learning data repository. That's some real messy data. Start playing around with that. Get comfortable clarifying problems. A good part of my day is clarifying the problem for people. And then pick an area to become an expert in. And you don't have to pick that from day one when you're graduating. It's fine to change, but in your career, try to choose things that you're going to become an expert in that area. Thank you very much. Oh, that is completely unreadable. That's my LinkedIn profile. It's simply J. Peach. It's just John Peach. If you want to connect with me on LinkedIn, I'm happy to do that. Thank you very much. I appreciate your attention, and I hope this has been very helpful for you.